Hello, welcome back to this video lecture of module 3. In the last videos we learned the Opamp applications. So we derived the expressions for the ideal inverting amplifier, ideal non-inverting amplifier, then the voltage follower, summer circuit or the summing amplifier, and the difference amplifier or the subtractor circuit. So we'll learn few more applications in this particular video. So let's start with the integrator. So integrator is a circuit whose output voltage is proportional to the integration of the input voltage. So output is the integration of the input signal applied at the input signal applied. So integrator circuit can be constructed using the passive devices or the active devices. So accordingly, so the circuit which is constructed using passive devices such as resistors, capacitors, etc. is called a passive integrator, and a circuit which is constructed using active devices such as Opamp transistor is an active integrator. So since we are learning the application of Opamp as an integrator, so this particular integrator circuit is an active integrator. So the circuit shows the integrator circuit, Opamp integrator circuit. So wherein the in the feedback, so we have the capacitor connected instead of the resistor. So the input signal is applied to the inverting terminal of the Opamp through the resistor R1, and the non-inverting terminal is connected to ground. So since the non-inverting terminal is connected to ground, the voltage at node B is equal to 0. And by the concept of virtual ground, so both the input terminals are at the same potential, are always at the same potential, hence VA equal to VB equal to 0. So looking from the input side, so we have the current I equal to V in minus VA by R1. So since VA equal to 0, so the above equation reduces to V in by R1. And in the feedback loop, so we have the current IF. So IF equal to CF into D VA minus V0 by dt. So since VA equal to 0, so the above equation reduces to minus CF dV0 by dt. So as the current into the Opamp is 0, so the current which was flowing through R1, so the same current flows through the feedback resistor as feedback capacitor as well. So thus I equal to IF. So now equating the two current equations, so we have the equation given by, so V in by R1 equal to minus CF dV0 by dt. So taking the differential term to the left hand side, so we have dV0 by dt equal to minus 1 by R1 CF into V1. So applying the integration or integrating on both the sides with respect to t, so we have integral of integral over the interval 0 to t dV0 by dt into dt equal to minus 1 by R1 CF integral of 0 to t V in into dt. So equal to V0 equal to minus 1 by R1 CF integral over 0 to t V in dt plus V0 of 0, where V0 of 0 is the constant of integration, or it is also it can also be stated as the initial output voltage when the time is equal to 0. So this R1 CF is called as the time constant of integrator. So if the initial output voltage is considered to be 0, then the above equation reduces to V0 equal to minus 1 by R1 into CF integral of 0 to t V in into dt. So thus the output is equal to minus of 1 by R1 CF times the integral of the input voltage. So this negative sign is due to the fact that the input voltage is applied to the inverting terminal of the op-amp through the resistor R1. So thus the output voltage is the negative integral of the input voltage. So if the input voltage to the integrator is a sine wave, then the output is a cosine wave, and if the input is a step signal, then the output would be a ramp signal, and if the input is a square wave, then the output would be a triangle. So applications of op-amp is, so it is used in the op-amp integrator is, so it is used in the analog computers, so it is used in the ramp generators, it is used for solving the differential equations, so used in the analog to digital converters, and it is also used for in various signal wave shaping circuits. Next is the differentiator circuit. So in this case, the output voltage is proportional to the time derivative of the input voltage. That is, output is the differentiation of the input signal at its output is a differentiation of the input signal. So the differentiator circuit can be obtained from the integrator just by exchanging the resistors and the capacitors. So here the capacitor is connected to the inverting terminal of the op-amp. Input is applied to the capacitor, and in the feedback part we have the feedback resistor. So, and the non-inverting terminal is connected to ground. So hence at node B, so the voltage is equal to 0. So therefore VB equal to 0, and by the concept of virtual ground, so VA equal to VB. So since VB equal to 0, VA is also equal to 0. And looking from the input side, so the current I1 is equal to C1 into dV in minus VA by dt. So since VA is equal to 0, so I1 equal to C1 into dV in by dt. And in the feedback loop, so we have current I1 equal to VA minus V0 by RF. So since VA equal to 0, so equation reduces to minus V0 by RF. So as the current into the op-amp is equal to 0, so the current which was flowing through the capacitor C1, so the same current flows through the feedback resistor RF as well. So thus I1, the current in the input side as well as in the feedback loop are same. So thus equating the two current equations, so we have the equation given by C1 into dV in by dt, so equal to minus V0 by RF. So rearranging, we have V0 equal to minus C1 RF into dV in by dt. So the negative sign indicates a phase shift of 180 degree between input and output. That is also because the input is applied to the inverting terminal of the op-amp. So thus output is C1 RF times the differentiation of the input voltage, and C1 RF is called as the time constant of the differentiator. So if the input signal is a sine wave, then differentiation of sine would result in a cosine signal. So if the input is a step signal, so then the output is a spike, and if the input is a square wave, then it results in a train of impulses. So the square wave, like if the input is a square wave like this, then the output would be like this, a train of impulses. So step in the sense, if the input voltage is just like this, then the output would be a negative spike. Okay. The applications of the op-amp as a differentiator is, so it is used in the wave shaping circuits to detect the high frequency components that are present in the input signal, and it is used as a rate of change detector in the FM demodulators. Okay, so these are the linear applications of the op-amp. So where output varies linearly with respect to the input. So the one of the non-linear application of op-amp is the comparator. So comparator, as the name indicates, it compares a signal voltage applied at one input of an op-amp with a known reference voltage at the other input. That is, input signal is applied to one of the input terminal and a reference signal is applied to the other input terminal of the circuit. So hence the two signals are compared. So based on which signal is greater or higher, so accordingly, so it produces output, so which is either high or low. Okay, so thus the output voltage in this case is either a positive saturation voltage, which is plus V saturation, or a negative saturation voltage represented by minus V saturation. So the op-amp in this case is used in the open loop configuration. So we'll study one of the comparator circuit, so that is the inverting comparator, so wherein the op-amp is connected in the open loop mode. So to the inverting terminal the input signal is applied, to the non-inverting terminal a reference voltage, that is a DC source is connected. So the voltages, these two are the voltages which are compared, and the supply voltages are plus VCC and minus VEE. When the input voltage is less than the reference voltage, then V0 is equal to plus V saturation, so which is approximately plus VCC. So here, since the input is applied to the inverting terminal of the op-amp, so the output is phase shifted with respect to the input voltage, and when Vin is greater than the reference voltage, then the output is minus V saturation. So thus for if the input is higher, then the output is a negative voltage, that is there would be a phase shift in the output voltage. So if the input voltage is less than reference, if it is a smaller voltage than the reference voltage, then it is represented by a positive voltage, that is there would be no phase shift. So here the waveforms shows how the output voltage appears. So initially we'll consider that the reference voltage is equal to 0. So here we have the input voltage represented by a sine wave with the reference voltage equal to 0. So according to this conditions, so when the input voltage is greater than reference voltage, then the output would be equal to minus V saturation. So thus input voltage, so here you can see the input voltage rises above the reference voltage. So as it rises, so as Vin is greater than the reference voltage for this particular point of time, the output is equal to minus V saturation, so which is approximately equal to minus VCC or minus VE. So you can note that the output voltage polarity is different, or it is opposite with respect to the input voltage. This is because the input is applied to the inverting terminal. So thus there is a phase inversion between the input and the output. So here for the negative cycle, so wherein for the negative voltages, that is for V in less than the V reference voltage, okay, so the output would be when V in is less than V reference, output voltage is equal to plus V saturation, that is it goes to the plus V saturation. So thus we have for the negative cycles output voltage represented by plus VCC. So this is for the case when the reference voltage is equal to 0. So now we'll see if a positive reference voltage is applied. That is when the reference voltage is greater than 0 volt. That is a positive reference voltage is applied. So this level represents the plus V reference voltage. So for this particular range of time, so we note that the input voltage is less than V reference. So input less than V reference. So when input is less than V reference, output is plus V saturation. So thus for this particular point of time, so the output voltage is plus V saturation. Output rises up to plus V saturation, or it goes up to the plus V saturation. Next, as the input voltage rises above the V reference, that is for this particular point of time we see that the input voltage is greater than V reference. So when V in is greater than V reference, then V naught is equal to minus V saturation. Output now reaches to minus V saturation. So thus for this particular point of period of time, output is equal to minus V saturation. And for the next period, that is from this part of the input cycle and the negative part of the input cycle. For the negative part of the input cycle, so we see that the input voltage is less than V reference. So when it is less than V reference, so V naught equal to plus V saturation. Thus the output rises to plus V saturation. And then again, as the input rises above the V reference, output voltage is equal to minus V saturation. So this is what the comparator, that is inverting comparator. So the comparator, what it does, it compares the two signals, that is compares the input signal with the reference voltage. So based on whether the input voltage is greater than the reference voltage or less than the reference voltage, so accordingly, so output voltage would be either output voltage reaches either positive saturation voltage or the negative saturation voltage. So that's the applications of the op amp. So thank you.